now moving on, we have cases where, okay, I'll just write it down. So now we're going to be examining infinite discontinuities at endpoints. Okay, so basically what this is saying, well, I'll write them out and then I'll explain them. So we have if f of x is continuous, and I'm just going to abbreviate here, continuous on, here's the interval, this is important, a has a closed bracket and b has an open one, and discontinuous at x equals b, that's why we have the rounded bracket, right? Then our integral from a to b of f of x dx is going to be equal to the limit, and we're going to use r again because that's a useful variable, I guess, rb minus, and I'm going to explain the notation here. Don't think that's a minus sign. Well, it is a minus sign, but it doesn't signify negative. So yeah, I'll explain that. And then a to r, because we just replaced the top, right, with r, and then f of x dx. Okay, so for this one, what this means, let's say we have a graph, right? So we have something like that. Okay, here's our x and here's our y. And then let's say here's a and here is b. Okay, so reading the beginning of the, I don't know if this is a theorem or I guess I'll just call it a rule. So it says if f of x is continuous on a to b and discontinuous at a equals b. So basically from a to b, this is all continuous except for right here. Let's say there's an open dot, right? So what this equation is saying is that the integral, so the area under the curve from a to b, is actually going to be, you're evaluating from a, so starting at a, and then we're taking the area underneath, and then what this b minus means, the minus sign means to the left of. To the left of. Okay, so what that means is we're going to be going along and then we stop right before that open dot. Okay, so think of b, like, let's say we have b equals 3 or something. Well, yeah, okay, let's say we're evaluating from 1 to 2, okay? What this means is that you'll actually, we're actually evaluating from 1, so let's say this is 1, and that's 2. I know this isn't drawn to scale, but, so this is 1, so we start at 1, and then we evaluate 1, everything up to almost 2. So we're going to go up to like 1.999999999 to infinity, basically. As many 9s as you can think of. But we're not evaluating it at 2, because at that value of x equals 2, then our f of x doesn't exist, because it's discontinuous there. Okay? Alright, so, yeah, and then we have the opposite. So this is when the top, when it's discontinuous at the top boundary or limit of our interval. But let's say we have, okay, so this is like a separate section here. If f of x is continuous again, continuous on, this time we're flipping it. So the rounded bracket goes at a, and the square one goes at b, but, and then this one's going to be discontinuous at x equals a. Okay, so now we have, this is what it looks like. So we have this, and then we're going to use our handy dandy r again, and this time it's as r goes to a plus. And this means, since the minus meant right, like on the very left of, this is going to mean to the right of, to the right of. Well, that was weird. Okay, this is an of. Looks like elf or something. Okay, hold on. I have to fix this. To the right of. There we go, that's better. Okay, and then we have our r goes down here now, and b is at the top, f of x dx. So I'll draw a quick little graph down here so you can visualize it. So now we have a and b. Here's our x and y. So this is a, this is b, and now the function is discontinuous at a. So this a plus means we're going to start to the very right of the a and then evaluate all the way up to b. So in this case that we took before from 1 to 2, now we're going to have, I'm going to go right down here and squish it in. So let's say we're evaluating on this interval. So we're not evaluating right at 1, but we can start at 1.00001 and then all the way up to 2. Okay? All right. Now, let's do a quick example of this, and I will start on the next slide. Okay, so let's say we have the given integral. So we're going to integrate from 0 to 27 of 1 over the third root of x, and then dx. Okay, so here, as you can see, if you were to plug in a 0, so f of x equals 1 over third root of x, right? And as you can see, this is continuous on the interval except for at 0. If we were to plug in 0, we would get 1 over the third root of 0, which is 1 over 0, which we can't have, right? This is undefined. So what this means is that our interval is actually going to be a rounded bracket for the lower one. And at 27, it's fine, right? That's just 1 over third root of 27. So we're going to be doing the second case from the last slide. Okay, so let's get started. If we apply the rule, then I'm just going to rewrite this. So third root of x dx. So this is where our limit comes in, right? And r is going to the bottom one. And we're going to start to the right of it, okay? Yeah, so this is going to, okay. So we're starting to the right of it since it's at the bottom. We're replacing this bottom limit. So then we're going to have r down here, and we're going to keep the upper bound. And then we have our normal function, okay? So then this is going to, now we're just going to evaluate the integral, and we plug in r at the very end, okay? So we're going to have limit as r goes to 0 plus. And this is a x to the negative 1/3. So we're going to get x to the 2/3, and we have to have a 3/2 in front for it to cancel out when we do differentiate. And this is evaluated from r to 27. Okay? And now we have, so we're just going to keep rewriting this limit in the front. It's very important. Okay, so when we plug in, we get 3 over 2 times 27 to the 2/3. And then this is minus 3 over 2, and then r to the 2/3. Okay? And then now we have, we can plug in our 0 for r. So we get 3 over 2, and then this 27 to the 2/3. The third root of 27 is 3, and then that squared is a 9. And then we do minus 3 over 2, and we're plugging in 0 for r now, because we can do that. It's not on the bottom anymore, so this is fine. And this term actually just becomes 0 itself, so then we get 27 over 2 as our answer.